Back when we were studying integers, we talked about divisibility of integers. That was one of our main topics. What we're going to do now is to do the exact same concept, but in the context of polynomials. So we're going to look at divisibility of polynomials. So first we're going to define what it means for one polynomial to divide another. We'll study some examples, and then we'll prove a theorem, just to demonstrate how to use the definition. So recall the definition that we had for divisibility of integers. If m and n are integers, we say that m divides n. That's written m with a vertical line, then n. If n is equal to mk, where k is an integer. There are other ways of saying this. You can say n is divisible by m. You can say m is a divisor of n. M is a factor of n. And n is a multiple of m. And it turns out if we replace integers with r of x, we get a very similar concept. So let R be a ring and let P of x and Q of x be in the polynomial ring R of x. We say that P of x divides Q of x, and we write it in using very similar notation. If Q of x is equal to K of x times P of x for some K of x and R of x. Right? So basically every time you see an integer in the definition of divisibility of integers, you replace it with a polynomial for divisibility in polynomials. So there are other ways of saying this, similar as we did for integers. Q of x is divisible by P of x. P of x is a divisor of Q of x. P of x is a factor of Q of x. Things like that. So as with integers, we can factor polynomials to determine divisibility relationships. That was one of the big ways that we figured out which numbers divided which integers by doing factoring. So for instance, if you have this following polynomial in R of x, R being the real numbers, remember? You have x squared minus 5x plus 6. We can factor that into x minus 2 times x minus 3. And that tells us, for example, that the polynomial x minus 2 divides x squared minus 5x plus 6. Same with x minus 3. One of the tricky things in this situation is divisibility can depend on what we consider to be the coefficients, right? So if we're looking at this polynomial, same polynomial, now I'm writing it slightly differently, 2x minus 4 times 1/2 x minus 3/2. If you want to know how I did that, I factored a 1/2 out of the x minus 3 and then multiplied it by 2 to get to the x minus 2. So it's just playing with some constants. In R of x, it's clearly true that 2x minus 4 divides evenly into x squared minus 5x plus 6. But we could also consider x squared minus 5x plus 6 to be a polynomial in z of x, because the coefficients are integers. In that case, 2x minus 4 does not divide x squared minus 5x plus 6, because the polynomial you have to multiply it by to get to x squared minus 5x plus 6 is not a polynomial with integer coefficients. All right, now we're going to prove a very basic theorem. This theorem should look familiar. We proved a very similar one for integers. If R is a commutative ring, and if P of x, Q of x, and R of x are polynomials, if we assume that P of x divides Q of x and Q of x divides R of x, then it follows that P of x divides R of x. All right, so we know that P of x divides Q of x. That means that Q of x equals K of x, say, times P of x for K of x in a polynomial. And similarly, Q of x divides R of x, which means that R of x equals some polynomial M of x times Q of x. Well, notice that we can substitute the expression for Q of x in that first equation in for Q of x in the second equation. And if we do that, remember our R of x is equal to M of x times Q of x. We have that Q of x is K of x times P of x, so we can substitute that in. We can rearrange the parentheses so they're to our liking. So now we have M of x times K of x times P of x. And that satisfies the definition of P of x dividing R of x, right? Because we know that M of x times K of x is a polynomial in R of x, and that means that P of x divides R of x. All right, so it looks like you're ready to work on the in-class activities. The name of the file that you're going to be looking at is Introduction to the Divisibility of Polynomials, but there's also another one that goes along with this video once you finish those. That's called More Divisibility of Polynomials, included with this video.